we're going to go ahead and jump back in on 1.4 and take a look at intermediate value theorem and then try some practice problems with really everything in continuity and then intermediate value theorem. So remember, intermediate value theorem, you can abbreviate it universally as IVT. So anytime that you're using it. So IVT, now the idea of intermediate value theorem simply says this because everything's based around this idea of continuity. So that's why it's in this section. So if you can prove, which we know how to now using the three things, f of a is defined, the limit as we approach a exists, and those two values must be the same. If we can show that a function over an interval from, let's say, a to b satisfies those three conditions from a to b, if we know that a function is continuous over an interval, then what we can say is that anything that's sort of A and B straddle. And that's what I a lot of times use for IVT is this idea of straddling. So you can see here that the value at A, so when I say the value of A, we're talking Y value, so f of A. And then here's B over here, and so the Y value for B is up here. So what I mean by straddle is those two values, f of A and f of B, do they straddle whatever we're trying to show that's going to happen? So the question is, the chicken crossing the road. Well, if my values straddle the road, in other words, it's the chicken starts off on one side of the road and eventually ends up on the other side of the road, it seems so common sense, but the question is, did they cross the road? Did the chicken cross the road kind of thing? And the reason why is because of IVT when they ask the question. Because there's no way the chicken, it can avoid the road as much as possible, but in order to get over here, it has to at some point cross the road at least once. Remember, it could cross it a whole bunch of times, but it has to cross it at least once. And that's what IVT is saying. It's a very intuitive theorem dealing with continuity. And so what we want to be able to show is we've got to show that straddle. And so that we can get this, we got to also show that the function is continuous, so that we can use IVT. So there's a few things that we've got to be able to show as well. And again, that may come back to you from pre-calc. So let's dive into a little bit more of the definition. So if f is continuous on the closed interval a to b. So in other words, we have this interval from a to b. These are my x values. Okay, and it says the function is continuous. So that's the key. If f is not continuous on the closed interval. Now, it may not be continuous outside of it, so maybe there's a discontinuity way over here, like a hole or something like that. It doesn't matter because we're only looking at sort of this window between A and B. So as long as it's continuous between a closed interval A and B, that means it has to be defined at A and B, that closed part, okay? And then it says a k is any number between f of A and f of B. Okay, so f of A is whatever my y value is. So let's call this one f of A, kind of thing. And B, f of B is going to be whatever my y value is for my x value B. So what k is the road. Okay, that's what we're saying about k. K is the road. So k is some other y value somewhere between f of A and f of B. So somewhere on the y-axis we have some k value. We'll put it right there. So there's k right here. So if I went ahead and sort of just drew a dashed line as my road. So think of it as like a road. So if f is continuous on the closed interval a to b and k is some number between f of A and f of B, then there has to be at least one value c. Okay, there's a lot. They're just throwing. Now I use c over here, so I'm going to go ahead and eliminate my c that I had earlier so that doesn't confuse you. Okay, but what we're talking about here is now we're talking about an x value. There has to be some value x. In other words, there has to be some point where the chicken crossed the road. There has to be somewhere. I don't know, maybe here. But there has to be at least one x value where as the chicken gets closer to the road, it's going to cross right there at the x value of c. And so what they're saying is a number c in the interval a to b, so there's my x value, such that f of c equals k. So in other words, it's the road. So if this is continuous, there has to be at least some x value that when I plug it in, it's going to equal k. Otherwise, we didn't cross the road, and how did we get from one side to the other type of thing? And so we want to go ahead and think of IDT as more of a straddle type of theorem. We got to show that we're somehow have a value that's larger and a value that's smaller than whatever value they're asking me about, okay? And so use the intermediate value theorem to show that the polynomial has a zero in the interval. Okay, so to use IVT, so I'm going to put, this is a flashcard. To use IVT, what do we have to show? We have to show that the function is continuous. So we have to show the function, I'll just call it f of x, is continuous. Now, how do I show something's continuous? I show something's continuous by showing that the value is defined, that the limit exists, and that they're equal to each other, okay? Now, over an interval, how do I show a function is continuous? Well, a lot of times it's either stated, f of x is continuous, over an interval, or, like in this case, that right there gives it away. And so we have a polynomial function, f is a polynomial. So for this specific example, number one, how do we show that f is continuous? What we'd say is, since f is, sorry about that. So since f of x is a polynomial, or maybe a better way of putting it, let me write out that it's not working so well. So let me write it up here. So what do we got to show? So IVT, number one, we got to show the continuity. Okay? And so for this specific example, we would say f of x is continuous since f of x is a polynomial. Good. Number one done. So we showed that f of x is continuous on the closed interval. Okay, so f of x is continuous over the closed interval. So let's make sure I put that over the interval over, what is it, -1 to 2. Since, so sorry, I should have added that in. Since f of x is a polynomial. Okay, so we showed that it's continuous over the interval. So make sure it's continuous over the interval. So whatever interval they give us, we have to make sure it's continuous over that, because it may not be continuous everywhere. And that's what I said earlier. So we've got to just show it's over the closed interval. So it's this is f of x is continuous over the closed interval -1 to 2, since f of x is a polynomial. And continuous everywhere at that point. Okay, number two, what we've got to do is we've got to show the straddle. So when I say show straddle, what I mean is you want to find what is f of a and what is f of b. So in this case, our a and b are two values, are two x values, so -1, 2. So I want to show what's f of -1, and I've got to find what is f of 2. So that's what I mean by showing the straddle. So find your two values. So f of -1, we plug -1 in and we end up getting 3. When I plug 2 in, I get 2 minus 8, which is -6. Okay, so there's my values. So the question is do I straddle whatever value they're asking about? And they're asking us if there's a 0. So in other words, does f of x equal 0 at some point? So do these two, is my road is 0, and I have a value at 3 to start. So it's up here. So my dot's way up here. And then I get a value when, at -1, I get a value of 3. And then at 2, I get a value of -6, which is down here. And then 0 is my road. And so the question is, does the chicken cross the road? And the answer is yes. And how you defend that is you're saying, look, IVT proves it. Because the function is continuous on the closed interval -1 to 2. F of -1 is 3. F of 2 is 6. I straddle, so there has to be at least 1 0. Do I know where it is? No. I have no idea where it is, but I do know at some point I at least get 1 0. And this is called an existence theorem. It doesn't tell us where it occurs. It just tells us it exists somewhere, kind of thing, or at least at one point. Looking at the last example here, I have shown that this is root. Remember, the word root is the same thing as a 0. So it's going to be very similar of a process. I'm going to delete everything I have up right now. And what we got to do is we've got to figure out what is f of 2. We got to show the straddle. We got to make sure that this function is continuous over that closed interval. And so we're going to find f of 2. And then, so the first thing is f of x, is that continuous? Well, there is a point of discontinuity, but it's at -1. And so if you notice, -1 is not in my interval. So therefore, this thing is going to be continuous. And again, how we can show that is just say the only discontinuity is -1. Therefore, it's continuous. So f of x is continuous over the interval 2 to 3. That's my interval I'm looking at. 2 to 3. So we've stated this continuity. Then what's f of 2? We plug in 2, we get -1 on top, we get 3 on the bottom, so we get -1/3. If I plug in 3, I end up getting 4 on the top, and I get 4 on the bottom, which is 1. And the question is do I straddle 0? You know, will 0 fit in between these, or is it outside of those two? And if you notice, we go from negative to positive, so there's got to be a 0. So therefore, a root exists in the interval 2 to 3. Okay. I'm going to rewrite this a little bit better. Okay. What I'm going to say is IVT then guarantees and guarantees there exists a root in the interval. Make sure to specify the interval 2 to 3. So again, what we do is we show the continuity. Number 2, we show the straddle. And number 3, we state the IVT. So number 1, get the continuity established. Number 2, show the straddle, or figure out if there's a straddle. And number 3, if those two things are true, then we can go ahead and state our IVT. And that's how you would prove IVTs. Okay. Now what we're going to do is just sort of look at some examples. So again, you can pause, work through them yourself. I'm going to go as quickly as I can. And just go through these examples as best we can. It says, which of the following statements is or are true? The limit exists, the value exists, and it's continuous. Well, look, if the value exists and the limit exists and they're the same, it's going to be continuous. So I really need to find all these for it to be continuous. Now, if it was continuous to begin with, if I knew as a polynomial, then it's continuous. Doesn't that imply the value exists and the limit has to exist at that value? So there are ways to get this a lot quicker if we knew it was already continuous. But we don't. It's a piecewise, so we better make sure. So let's check with f of 1. I always like the function's value first. I find it to be the easier of the two. And so let's go ahead and check f of 1 and its value. So f of 1 means I'm going to plug it in here, and so it's defined to be 4. And then we want to figure out what our limit is. Now, this is a multiple choice, so we don't really have to prove it in this case. So I may just do the left and right in my head, or just show you over here. So this is interesting, though. This is a little different. As I come towards 1, I'm not at 1, right? So it's going to be something like 0.9999, something like that from the left. Well, if you notice here, that is this. 0.9999 does not equal 1. So we're going to be using door 1 to evaluate our limit. Now, we can't plug in 1. We got to simplify this, and so we have to factor. And when we do, we get a simplified expression of x plus 1 because the x minus 1's cancel. Okay, so what we have is when I plug in 1, I end up getting 2 from, let's say, the left-hand side and from the right. But look at what we have here. Is this thing continuous? Well, the limit exists because, again, from the right, 1.00001, let's say that's from the right, wouldn't that not equal 1? So whether we're coming from the left or from the right, we're using the top function. And so the limit is going to be 2, the value is 4. So does the limit exist? Yes. Does the value exist? Yes, it is defined. Is it continuous? No. So what we have is we have 1 and 2. And so that's an example of straight off of an AP exam. That a lot of these are. So that's why I'm trying to get you used to the multiple choice side of it. The second example, it says that, in this case, it says f is continuous. So they tell us it's continuous. We're having to make sure that it satisfies that statement. If f is continuous, what do we know? Well, then what we know is that f of 0 is defined. And we also know that the limit as we approach 0 is not just exists, but it also equals f of 0. So let's figure out if we know what f of 0 is. So f of 0 is simply k. See it right there. F of 0 is k. So we don't know the number. That's obviously what we're trying to find. But we do know what the limit is as we approach 0. Because from the left and from the right, we're going to be using this top piece. Because anything smaller than 0 or just a little bit bigger than 0 falls into this domain right here. So again, we factor. Because we can't just plug it. We try to plug in 0, but we don't have any success there. So we get and cancel. Now we should be fine. We have x minus 1 over 2. Now it allows me to plug in 0, and I get negative 1/2. So my limit is negative 1/2. So if the statement holds that the function is continuous, then what do we know has to be true about k and negative 1/2? And this goes back to our flashcard. This is why we got to get those down. For a function to be continuous at a point, the value has to be defined, which is k. The limit has to exist, which is negative 1/2, and those two have to equal each other. And so what we have is we just found the value of k is negative 1/2. Okay? Good problem. You'll have something in your text like that. Okay? Moving on, again, I'll go fairly quickly through these best I can. So we look and say, okay, which of the following are true, it looks like, kind of thing. And so what is the limit? The limit as we approach A is the same as we approach B. Well, the limit as we approach A looks like it's 2. So that's sort of answers it immediately, to be honest with you right there. But why is the other one's not true? Well, the limit as we approach B doesn't exist. There's a jump. There's a discontinuity. The limits don't equal from the left and right. So the limit doesn't even exist at B. So there's no way the limit can equal anything at B because that doesn't even exist. And then it says the limit as x versus A does not exist. No, it does. It's 2. The value is not defined, but the limit exists. Looking at another piecewise one, again, you'll hopefully get used to these as we approach negative 1 from the left. And if I'm talking left, I'm talking this piece. So if I plug negative 1 in, I get 4. From the right-hand side, I would be using this piece. So if I plug negative 1 in, guess what? I get 4. And then how do I know if a two-sided limit exists? The limit from the left has to equal the limit from the right. That's a flashcard. So our two-sided is also 4. Then I threw some logarithms at you, just keep those in mind. And there's a property coming up here, which is really good to look at. So it says, what's the limit as we approach 2? So we got to figure out what is it from the left and what is it from the right. So if I want to find what the limit is as we approach 2 from the left of this function, then what I'm looking at is which piece of the piecewise. Well, if you look right here, that is to the left of 2. That's smaller than 2. So I'm looking at the first piece, and I would do a direct substitution, and I get the natural log of 2. And that's as far as we can go. You don't need to put it as a decimal because this is probably a non-calculator problem to begin with. But then what we've got to do is we've got to figure out what is the limit as I approach from the right-hand side of 2 of the function. So the right-hand side of 2, we're using this piece, so I plug it in. And what you'll notice is what we get is 4 natural log of 2. Now, we can intuitively probably figure out these don't equal each other because one is 4 times natural log of 2 and the other one's just natural log of 2. However, so in this case, it doesn't exist. So let's answer the question first. However, I've seen these before where instead of looking like this, let's say instead of natural log of 2, you got the natural log of 16. Let's say it was something like that. Now, as we look at these don't look the same. I mean, obviously, they're not identical to each other when it comes to just as we look at them, but are they the same? And this is where our properties that we learned, and this is why it's so important to remember our logarithmic properties. This is the one where if there's something in front of a logarithm, we can make it an exponent. And so the natural log of 2 to the 4th is the same as 4 natural log of 2, and 2 to the 4th is 16. So you can see those are actually the same. So it would be continuous or something like that. So heads up on that. That's where some of your logarithmic properties come in. Last example is an IVT. And so again, it gets a little bit tougher, but keep in mind what you have to do. So we've got to make sure that the function is continuous first. And so here, f is continuous on the closed interval 0 to 2. That's just given to us. And so number 1, f of x is continuous. Now, we don't have to prove it because this is a multiple choice, but it's good to go through our list. The next thing is I've got to figure out what in the world's f of a and what's f of b. Now, our a in this case is 0, and 2 is our b. and we look at our table of values numerically to figure out what f of 0 is, and that is 1. F of 0 is 1, and f of 2 is 2. Okay, so there's like our road. We're at 1, to start with, and then we go up to 2 or something like that. And then it says the equation y equals 1/2. Okay, so 1/2 is actually below 1. So here's 1/2 right here. So that's what they're saying, y equals 1/2. So I'm going to put a little line here. That's the road. Okay, again, that's what we got to straddle. So right now it doesn't straddle, but that's not what they're asking. It says the equation f equals 1/2 must have at least 2 solutions. Now what that means is we have to touch this road twice, at least twice, in the interval from 0, which is what our f of 1 is, and then 2, which is what our value of 2 is. That's a little off, sorry. Do that again here. So at 2, we get 2. So what they're saying here is which of the following values will guarantee me that if I start here and I end here, that I'm going to cross this twice. So let's just look at some of the things that they have. 3. So if I go and say, well, does the y, so in other words, the equation, what does k have to be? What y value of 3? Well, if the y value is 3 is up here, okay? So in other words, which value guarantees this? So let's say my c value was 3. Does that guarantee that I cross that orange one to come up here and hit the red? No, I can do that. That just disproves it immediately. So 3 doesn't work for me. I have to be able, so what we're looking for is we're looking to straddle actually twice here. If this is my road, I've got to pick a value that is below the road so that I can cross it once, touch it, and then to get back up to 2, I'll cross it again. That's the only way to guarantee that I'm going to cross that road twice, which is what they're asking me to have 2 solutions. So which value guarantees me to cross 1/2 twice? It has to be below 1/2. And the only one that's below 1/2 is 0. 1/2 guarantees one solution, like I can touch, but it could have been a touch and turn. So it doesn't guarantee me 2. All of these could be 2, but there's no guarantee. So anything that's above the road, there's no guarantee, and we have to guarantee that. Okay? And that's IVT and the rest of continuity problems.